All right, well, welcome to this video. And what I've got in front of us here is kind of a combination problem. I'm not entirely sure that anything in your review will be this complicated, but I want to show you what's possible with these different angle postulates and theorems that we have discussed in class. I made them into cards, okay? And so there's some that you are very familiar with, and there's some that you probably haven't seen before. What I'm claiming, or what I'm curious about, is whether or not being given just these two angles, alpha and beta, here and here, being given their measures, that we would be able to find theta. Because right at first glance, it doesn't seem possible. So I want to go over a couple of things about how this is drawn, and then I want to jump into those flashcards so we can find the right card to solve the problem. First of all, these two arrows indicate that these two lines are parallel to one another, and these double arrows indicate that these two lines are parallel to one another. Okay? That was the main thing I wasn't sure everybody was aware of. So what we're going to do now is begin. Now, we can start either with beta or with alpha, but if you think about it for just a minute, you aren't free to start with alpha. If I put alpha in there at 97, I won't be able to solve the other two angles. I need beta first, and then I need to exploit a property that's visible right here to get into this triangle, okay? So what we need to do is we need to put here beta is 35 degrees, okay? So beta is 35 degrees, and that was just given to us, all right? Let me zoom in on this a little bit, okay? Now, is there a property, a theorem, a postulate that can help us bridge the gap between that exterior angle and the inside of that triangle? I want to highlight a little shape here, and that's this shape here. Okay? It is the shape of an X, kind of a skewed X. But when you ever see that shape, you have vertical angles. All right? Now, let's go to our cards. All right? No, not angle addition postulate. Not the alternate interior angles. The triangle exterior angles, no. Corresponding angles, no. Vertical angle theorem. Here we go. So let's see what it says. It says, definition, vertical angles are, and then it gives the symbol for congruent. And then it gives two examples. So you can see the X shape of these angles and how the sort of top and bottom angles are equivalent, and then the side angles are also equivalent. Applying that to this problem right here, this angle inside the triangle has to be equal to beta. Now, I'm going to call the angle inside the triangle angle 3. So I'm just going to call it angle 3. Okay. And we have to establish exactly what the directions are telling us to do in these problems. And they're telling us to certainly solve them, but that's only half of it. The other half is to defend what we're doing. Okay, so how did I'm going to now make a claim that the measure of angle 3, let me do this right down here. Okay, given, okay, that the measure of angle beta equals 35 degrees, okay, comma, using the, and here we can abbreviate VAT for vertical angle theorem. We find the measure of angle 3 equals 35 degrees. Okay? And that's what I mean by defending what you're doing. You have to write it out. Okay, so we're going to equals 35 degrees. Okay, so now I have two of the three angles internal to this triangle. I have alpha equals 97 degrees, and the angle 3 down here is 35 degrees. So I need to find, let's see, we've got alternate exterior, polygon exterior, no. Polygon angle, no. Triangle mid-segment, no. Parallelogram, no. Keep going, let's see. Angle bisector theorem, no. Consecutive interior angles, no. Complementary angles. You know what I'm looking for. Something to do with the triangle. There we go. The triangle angle sum theorem, or TASTE, okay, as we call it. Definition says the sum of the interior angles of a triangle is 180 degrees. All right, so now by TASTE, okay, you can say this was like step 1 down here. All right. So we can find this angle over here, which we're going to call angle 4. Okay, so I'm going to say two. According to, and then I'm just going to abbreviate TAST, according to the triangle angle sum theorem, the sum of angle 3, angle alpha, and angle 4 must equal 180 degrees. Okay? Now I'm going to use the symbol for therefore. 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 Okay? That's the symbol. Therefore, if the measure of angle 3 is 35 degrees, and the measure of angle alpha is 97 degrees. Okay, and now over here in side work, we need to find that sum. So we have 97 and 35. All right, 7 plus 5 is 12. And then 9 plus 3 is 12. Plus 1 is 13. I have 132. Okay, and I'll just make a note of that parenthetically here. I'm going to say 35 plus 97 equals 132. By taking the difference of 180 and 132. Okay, let's do that over here. 180 minus 132 is going to give us the measure of angle 4. Is it 48? Let's see. Yep. Okay, by taking the difference of 180 and 132, we find the measure of angle 4 equals 48 degrees. Okay? Now, is there a theorem? Let's zoom out now. Let's look at the picture. There's a lot of ways that we could get from where we are. So we now have this equals 48 degrees. There's a lot of ways where how we can get from where we are to theta up here. There's not like a wrong way, okay? So I want to show you a couple ways that we could get there. The most direct path is simply to notice that if these lines are parallel and the lines adjacent to them are also parallel, I don't have this theorem written down, but I can tell you that angle 4 and theta are the same. Okay? But let's say that you didn't know that. Okay? Let's find another way to prove it. I want to direct your attention to this angle right here. Okay? Right here. I want us to try to find this exterior angle right here. We're going to call this angle 5. There's actually two ways that we could find angle 5. I want to show you both of the ways. I'm actually looking at this now, and there's 3 ways we can do it. So, all right, first we have to find the theorem. Okay, so here's one way we could find it, the linear pair theorem. Okay, let's take a look at this. Two angles form a linear pair if their adjacent share one side and whose sum is 180 degrees. They're supplementary angles. Are these supplementary angles? Measure of angle 5, let's say angle 5 and angle 3, are indeed supplementary because the sum of the two angles will be 180 degrees. They also meet the definition of the subset of supplementary angles called linear pairs because they share a common side here, and they are adjacent to one another. So they are a linear pair. A linear pair is just a type of supplementary angle. Notice also that beta is supplementary to and linear pair to angle 5. So these are both 35 degrees, so that makes sense. Yet I want to show you something. So first, let's find, using this simple method here, we have an explanation here with the linear pair theorem. We can say down here 3, okay? By the linear pair theorem, we find the measure of angle 5 equals, and now we just have to do 180 minus 35. So we'll write that down, 180 minus 35. Okay, well, what is that? 180 minus 35. That's going to give us 45, right? Or 145. Okay, so we find the measure of angle 5 equals, so thus, the measure of angle 5 is 145 degrees. Okay? Now, I want to show you something cool. So, let's verify that, right? Like I say, I don't believe you. I don't believe your linear pair theorem, or I don't believe your supplementary I don't believe your supplementary angles theorem. Okay, is there something else? Yes, there is. There's some cool, this cool thing I'm going to show you right now. All right. Okay, so angle addition postulate, no. Alternate interior angle theorem, no. But this one is it, okay? I call it teeth. The triangle exterior angle theorem. The measure of each exterior angle of a triangle equals the sum of the measures of its two remote interior angles. Is this applicable to our problem here? Like, what I'm suggesting is that that angle is angle 5. This alpha corresponds to that red angle, and this green corresponds to angle 4. So I think the measure of angle 5 is 145 degrees. So if I add together 97 and 48, will I get 145? Let's say 97 plus 48. 7 plus 8 is indeed 15. Carry the 1. And I got 9 plus 4 is 13, plus 1 is 14. 145. It works. So, I could put in parentheses here. Also, by teeth. So it's TEA and then th is just theorem. So it's triangle exterior angle theorem. Just mention that you could use that to confirm. Okay, there's typically always more than one way to get there. So we're sort of moving closer to theta. Remember, we think theta is 48, but since we don't have a card that tells us the specifics about the double parallel lines, we're going to have to do it a different way. So we got to now have to find this angle here, which we'll call angle 6. All right, so the question is, what relationship exists between angles 5 and 6? What do we call that relationship? I want to show you this card here. This is what I meant when I said this is kind of like playing magic. I play this card, same side interior angle theorem. Okay, also called consecutive interior angles. Two angles on the same side of a transversal that cuts two parallel lines are supplementary, and their measure of their angles sum to 180. What? Let's go over that again. Basically, you've got two parallel lines, and now you've got two angles that are sort of facing one another. If you have a situation like that, the sum of those two angles is 180 because they're supplementary, all right? There are two theorems which are essentially identical, okay? So let's just take a look at both of these at the same time. So we have the same side interior angle theorem and the consecutive interior angle theorem. Let's read consecutive interior angle theorem. Definition: if a transversal, that's just this blue line here, by the way. A transversal is a line, it's the word that is used typically in conjunction with parallel to say a parallel line's cut by a transversal produces these effects. All right, if a transversal intersects or cuts two parallel lines, each pair of interior consecutive angles are supplementary. All right, so if you already know that supplementary equals 180, then they add to 180, then you can kind of see that both of these cards are kind of like basically the same, right? Since it even says in SSIAT, it says same side interior angles are also called consecutive interior angles. So yeah, these cards are identical in what they're defining. So we're gonna I'm gonna go with consecutive interior angles. Okay. Let's say kind of run out of space down here. We'll pick up with step 4 over here. By the consecutive interior angle theorem / same side interior angle theorem, okay, the sum of angle 5 and angle 6 equals 180 degrees. Okay? So what you do is you say, well, now, angle 5 is 145. We already proved that, okay? Angle 5 is 145 degrees. Therefore, the measure of angle 6 equals 180 minus 145. Or, now we're going to do the work, right? I'm down here now. 180 minus 145, 35, okay? Or 35 degrees, okay? Now, there was another way we could have known that. We could have thrown down this card, the corresponding angles theorem. It says here, if a transversal intersects two parallel lines, the corresponding angles are congruent. What are corresponding angles? Well, we have two parallel lines cut by a transversal. Angle 6 and beta are corresponding. So we could have just seen that and said angle 6 is 35. What's nice is it's not that we didn't notice this. How sad. It's that we can use multiple theorems to verify what we're doing. Okay? So we can actually write and just say, also by CORR, corresponding, and then A dot T dot, also by the corresponding angle theorem. Okay? So angle 6 equals 35 degrees. Okay, so I want you to look very carefully at this picture. How am I going to get from angle 6 to theta? Like, what can I do? All right, I'm going to give you a hint. So it's going to be that corresponding angle theorem. So the corresponding angle theorem tells us that corresponding angles and where there's transversals and parallel lines are congruent. So I actually have corresponding angles here. The measure of angle 4 is 48 degrees, and so is this angle right here, which we're going to say is lowercase epsilon, okay? So equals 48 degrees. And I'm kind of going to inset the justification here by CORR dot A dot T dot. Okay, so now, if this is 48 degrees, I now can jump over here and say that this is 48 degrees because these are corresponding angles as well. Theta is corresponding to epsilon, all right? But is there yet another way that we could find it? I mean, I really like that method. There is something we could do, and it's just to shift this line over. Like, keep it parallel and shift it over and have it cut through here. Like, the way I'll do that is I'm going to say and dot it in like this. And let's see if that helps us at all. Well, I suppose, all it does is it just brings this 48 in a little bit closer, doesn't it? And it also gives us a chance to test whether 35 plus 48 leaves behind 97, which should be that angle right there, right? Because look, inside the triangle, 35 plus 48 plus 97 equals 180. So there's this 35, 48, 97 relationship going on. So anyway, I think we've proven by corresponding the corresponding angles theorem that this theta over here is 48 degrees. So what we're going to say is equals 48 degrees. We're going to say here, to defend all of this, 5 by the corresponding angle theorem the measure of angle epsilon equals 48 degrees. Okay? 6. Observe that angle epsilon and angle theta are corresponding. Okay? Therefore, by the corresponding angle theorem, we conclude that the measure of angle theta equals 48 degrees. And then we're done, right? So we're going to put this black box. It's a black square, okay? It means end of proof. Because you proved it, right? You use theorems to prove it. You're done. Now, as I said, what I just showed you was like the combination of 10 problems in the actual review. But I wanted to try to show you as many different use as many of those cards as possible in a single problem. And I kind of made this up because I thought, well, it'll let me use a lot of cards. And we did. We used 1, 2, 3, 4, 5, maybe 6 cards in there. I don't know, 5 or 6 cards. So we'll get a chance to see all of them. But I'm going to stop the recording there, and we'll pick this up again with the actual review. But that is this little mini lesson here, this little example, is how we're going to do that review. Okay? We're going to defend our work. We're never going to do something that isn't backed up by a theorem or a postulate, some justification, in other words. All right? That's how geometry works. It's actually how mathematics works, but geometry is kind of where you start to learn about justification. Okay? So let's end the video there, and I hope you found this a helpful introduction to what we're about to do on a much grander scale in the big review. See you in the next video.